Hello, cutie patootie, math angel. Welcome back, and a very warm welcome to Decaf-Math ASMR if you are new around here. Today, let us relax, and review how to find the area between two curves. And this is a topic from a first calculus class, probably, maybe AP, Calculus AB if you're taking that. And I thought we would just focus on building some intuition here and looking at the main formulas. Now, I'm going to say ahead of time that I want to focus on the area part. We are going to get integrals here, and I don't want to distract us by actually calculating the values of them, especially in this case. These are all polynomials I'm seeing here, so our integrals are going to be integrals of polynomials, which are relatively straightforward to calculate, and it's really nothing more than just using the backwards power rule formula for derivatives. So I'm going to make a separate video where we can practice that together as well for anybody who might be intimidated by it or feels like they need more practice. There's no shame in that at all, but I just think it's one of those things where it looks more complicated than it is, and I don't want us to get distracted from this particular review by just getting intimidated with a lot of calculations and numbers and everything. But we will come back to that, okay? I just wanted to give you a heads up and hope you're okay with it. But as always, it doesn't matter whether or not you're learning this stuff. If you've ever learned it in the past, or if it's been a while, or maybe this is a piece of cake for you. I just hope that we can sit back and relax, and enjoy this together, okay? It's not meant to be like a formal lecture or anything, but I think you know that. Okay, so the main formulas are actually very straightforward, but I think it's one of those things that is easy to complicate and get confused by, because especially with like AP Calc AB, they really try and mix you up with this stuff. So the formula works out to be like this, but there are a lot of different situations that are hidden within this. So first of all, to find the area between two functions, we can name the top one f of x and the bottom one g of x. So I don't mean like in this case we have y equals 2x squared minus 8x plus 10 and y equals x squared over 2 minus 2x minus 1. I don't literally mean this first one is f of x and the second one f g of x. I mean that it'll depend on the actual graphs themselves, graphs of these functions. So you'll see here we have two parabolas, and it's up to us to determine which one is this one and which one is this one. But if we're finding the area between two curves, there will be a clear top one and bottom one. Okay, and so we can determine which one based on the functions that we're given, or which one's to the right or left if we're doing like this version of it, a horizontal looking group pair of them. There's going to be one to the right and one to the left, and in that case we're talking this way. Okay, but we're going to label f of x as the top one and g of x as the bottom, or f of y as the right one and g of y as the left one. And it's important to know which interval we're talking about. So from a to b would be our x values, and I'll get into that. Sometimes we have to break the interval down, but in this case we're talking about there being a top function and a bottom function over an entire interval a to b, or a right one versus a left one over the interval c to d for y. Okay, so you label which one is f and which one is g, and in fact that's pretty much most of the work for this kind of question. Okay, so why is it like this? Well, I think the most straightforward depiction of this would be if f and g are positive, both positive. So let's say we have x and y axes, right? So let's say we have f of x is my top function. So let's say I have something like this, okay? And then how about just something like this, g of x? So you can see that these two functions are both above the x-axis over the interval from a to b. Okay, so if you've learned about integrals, which I'm assuming that you have looked at a first definite integral, if you're looking at this kind of question, you probably know about definite integrals like this. This is actually an infinite sum that tells us the area between my function and the x-axis, and we'd have to get into Riemann sums, but basically it's an infinite sum of areas of rectangles to help us approximate, and once we take the limit, it gives us the exact area under this f of x function and the x-axis, right? Okay, so we would have this entire area here beneath f of x and above the x-axis in this case, because f of x is positive. Okay, so this tells me the area. Now, same thing for g of x. So from a to b, the integral of g of x dx from a to b also tells me the area below g of x and above the x-axis, right? So this bit here, right below and above the x-axis. Okay, so if I subtract this bit away from this whole thing, what am I left with? Well, I would be left with just the area here, which is between f and g. So I'd be left with what we are looking for. So the light blue is this whole entire region, the whole thing. And then I subtract out this bit here. So I'm left with just that bit, which is indeed the area between f and g. So we're looking for the area that's below f of x and above g of x, since we said that f of x is going to be the upper one and g of x is the lower one. So that's the most straightforward look for this case, is if they're both positive, and just based on properties of the integral and really just limits, we can combine this to be f of x minus g of x dx from a to b. Okay, so I think where it starts to get a little bit confusing is if we have one or both functions being negative over the interval. So let's say we have f of x, and let's say we have g of x like this from a to B. So we have this. So you can see over this particular interval from A to B, we have f of x, which is positive, and g of x, which is negative here, right? So the y values are negative for g of x. So what happens here? Well, if we want the total area between f and g, you can see that we actually have like a larger area, right? We're basically taking this part and we want to add this. So when we're talking about area, in this case, we are talking about the total area. Like area in general is going to be a positive number. We're not looking at the net area. So we're not doing net as in if we have an area that's below, that would be a negative value. We're not looking at that. We want this to be a larger area. We want this thing plus this thing. So for this one, we had the total area and then subtracting out this. But if we have something down here, we want to add. So this actually takes care of itself, because when we look at A to B for this bit, okay, that's exactly as normal. It would be between the x-axis and my function, so this definite integral would give me that area. If I look at g of x dx, the integral from A to B, this is interesting. So this would not necessarily give me the area. It is almost the area, but it is going to be negative here. So this would be what would be called, like, if we added them, it would be the net area, right? But we want this total area together, so this is going to be a negative number. This is going to be a negative number. So when I subtract, it's going to be minus a negative. So that gives us the positive value, which is the positive area. So it takes care of itself because we are subtracting a negative number, which gives us plus. So that means that this would give us the total area. It'd be light blue plus purple. Okay, so in a way, this minus sign, the minus sign, actually still works out. So we still have the same formula. Okay, so I say that because our first question here, over this interval, we have this one's positive and this one's negative. So sometimes it's easy to get confused if we have to do this part plus this part, or this part minus this part, or which one's which and over what interval, and if we add or if we subtract. So the question is to find the total area of the shaded region, not the net area. So we're not going to get something small or negative. We're going to get this plus this value, absolute value. And because we're talking about absolute value, the definite integral helps us to determine that area, but sometimes we have to do the absolute value. So in this case, the minus of this formula actually takes care of it, and we can kind of sketch out the last scenario. Since f is always above g, we're either going to have them both be positive over the interval we're talking about, or f being positive and g being negative, or they might both be negative, right? So we might have something like this, and then maybe something like this. So they're both negative on this interval A to B. And of course you can extrapolate this for the C to D and the horizontal version for this. But But in this case, if we were to do a to b f of x dx, the integral from a to b, that would be not the exact area, it would be the net area of between f of x and the x-axis. So that would be here. So if we were to actually do the Riemann sum for this bit, it's not going to give us the exact areas because the heights of the rectangles are all going to be negative, right? So we would get a negative area for this if we did this integral, right? So we did height times width, but that would be a negative number, but that's okay. The definite integral is going to be negative, but we want there to be a positive area between these two. So that's also going to work out, because if we do the integral of g of x dx from a to b, we would get the whole thing, the area from g of x to the x-axis here, like so, right? That would be this whole thing. And so this is a little sketchy math, but it's okay. I think it'll give you the idea. This is going to be more negative. So f of x, this first one, is going to be this bit, and that's going to be negative. And then we're going to subtract something even more negative. So that leaves us with this little bit here in between f and g of x. That will be this bit here. Okay, so still the minus g of x still takes care of itself. In other words, we don't have to worry about doing the absolute value of this and then the absolute value of this. We can still just go ahead and follow the formula of top minus bottom. If you have your own preference for doing this, if you want to do absolute value and then finding the difference or whatever, that's totally fine. Just make sure that you are clear with when you choose to do that, so that you're not double counting something or adding something that you should be subtracting. But all in all, you could just flip this and find the difference between the two, and that's okay too. But if you want to just follow a single formula here, it really is just top minus bottom, and then make sure you have the intervals correct. Does that make sense? I hope that makes sense. Okay, so that's why these three different situations are kind of hidden within this one single formula. But that's actually quite nice, because then we don't have to think twice. So when we do that, make sure that the question, of course, the question has to be to find the actual area. So we're not talking about net area here. We're not talking about the value of a definite integral. We are talking about finding the area. Okay. Alright, so now that we have these formulas, let's go ahead and apply them for this. And should emphasize that we are talking about a particular interval here from a to b, but if we're talking about the area between two curves in general, or over a certain part here, for instance, we'll get an example here, but sometimes we have to break an interval up into smaller intervals so that we have a clear top and bottom function, because sometimes the functions cross over themselves in a way that over one particular interval, one is above the other, but on another interval, the other might become on top of the other as well. So we have to split that up to apply this formula. So this is just a general from A to B, but sometimes you have to interpret the functions in the interval differently, okay? So we'll get practice with that too, but that is just conceptually all we'll need for this. So now we have for this first question, we have two parabolas, y equals 2x squared minus 8x plus 10, and y equals x squared over 2 minus 2x minus 1. So those are parabolas, because they are quadratic functions. We have an x squared term, x squared, okay? These are standard forms for quadratics, ax squared plus bx plus c, right? So a is 2, b is negative 8, c is 10, a is 1/2, b is negative 2, c is negative 1. They're not in vertex form for parabolas, but we don't care, it's okay. And then we have x equals 1, which is this vertical line, and x equals 3, which is this vertical line, and you can see it lined up here. There's a 1 and 3. The origin would be right here, so moving one space is 1, and moving to 2 and 3, 3 would be right here. So which one is which function? Well, in this case, with our understanding of parabolas, we would know that this one has a coefficient of 2. So that means it is more narrow. This one has a coefficient of 1/2, so it would be wider because it is less than 1. So our standard parabola is just y equals x squared, which is centered at the origin. And then relative to that, a coefficient of 2 would be narrower. So that means this one is our f of x, and this one is our g of x. Well, no, that's always true, because the top one's f of x, but by that I mean this one is our f of x, and this one is our g of x, because of this coefficient here. So when you factor out an a, and then you complete the square and all that, your coefficient will be this 2, so that means this is a more narrow one. So this is our pink, and then this will be our whatever, our other one. So how about purple, because this is 1/2, so we have this. Okay, so now we've determined which one is which. Okay, and actually, for anyone of our dear friends here who might be colorblind, I'm sorry. Here. There you go. Oops. Okay, so x equals 1 and x equals 3 here, right? So the area between them is just going to be this top function minus the bottom, and as you see over this interval from this picture, this is the area between them. Then over that particular interval from x going from 1 to 3, the area here is clear that f of x is always above g of x, so there's no crossover. So we just do 2x squared minus 8x plus 10, and then minus x squared over 2 minus 2x minus 1 dx. Okay, that's it. So this would be our f of x, and this would be our g of x. Okay, and that's it. So now as far as calculating this integral out, like I said, I will do this as an exercise in another video, but all you'd have to do is go ahead and distribute this negative sign. That's a -1 times everything. You can combine like terms, right? So you could do the x squared terms, the x terms, and the constant. Then when you take the integral, the only, backwards power rule is just that the integral of x to the n would be x to the n plus 1 over n plus 1. So if you had an x squared, then you'd have x cubed over 3. And if you have a constant in front, you can go ahead and pull that out. That's just one of the properties of the integral. And you can also do each piece one at a time as well. So it's kind of distributive in a way. And that's just all based on our limit rules. So breaking this down is just all about calculations, right? So you go ahead and apply this, and then what you do is put in 3 for all the x's and get a value, and then minus, and then you put 1 for all the x's and you should get a number there, okay? And so this part is like plug and chug. It looks messy, and when you work it all out, it might look messy, especially when you do the plugging in, but it's actually just calculations, okay? And like I said, I promise we'll take time to actually do it, but I didn't want to scare you. I just want to focus on this setup here. So it's not so bad, right? We don't have to do any more than that. We don't have to actually break this up into rectangles or any of that stuff. We just go ahead and plug and chug. Okay, so here, number 2, we have x equals 2y squared plus 12y plus 19, and x equals negative y squared over 2 minus 4y minus 10, and y equals negative 3 and y equals negative 2. So here we have x as a function of y, so it's kind of like a horizontal situation here, right? So we're just going to want to determine which one is which one's to the right and which one's to the left. So again, they are both parabolas, and we can use a similar trick that this one has a coefficient of 2, which is going to be narrower, and this one has a coefficient of negative 1/2, which is wider, and also negative. So if we actually kind of flipped this way, it'd look like this and this. So in other words, we'd have negative values here, negative x values, and our origins right there. So the one to the right is our f of y, and that would be this 2y squared one. Okay, so again, in this case, they just so happen that the first function is the one to the right and the upper one, but that's not always the case. Okay, so you just want to be careful based on your graph. And if you're not sure, and let's say you're not given an actual sketch, then you can actually pick a few values, perhaps, like pick a value inside your interval here, and let's say 2, and see what f of 2 is, and see what g of 2 is to determine that. But you just have to be a little careful to make sure that you know in some way that they don't overlap within this region here, because then you might have just coincidentally picked one that was above the other, but there might be an overlap. So you have to at least convince yourself that, or maybe have a graph on your graphing calculator or something like that, have an idea. But in this case, it's not so bad because we're given these pictures. So we have this is our f of x to the right, and then this is our g of x to the left, and here we want y equals negative 3 would be right there, the bottom one, and y equals negative 2 would be here. And it is important that when we set up this integral, it's going to be dy, oops, I meant f of y and g of y for this one, right? So when we do this one, we have the whole thing with respect to y. So when we write out the actual a to b or c to d, it actually has to be the y values. So y going from negative 3 to negative 2, that can be kind of confusing too, because if you've been doing a bunch of questions like this and you do x values, you might be tempted to do something like negative 4 to 2 or something like that, or whatever. It might be kind of confusing, but we are looking at horizontal lines, so we want to keep it consistent. The y values will go from negative 3 to negative 2. Okay, so that'll give us the area between these two over this interval. And again, we have just f of y minus g of y, all within the interval. Okay. And so again, this is going to be a polynomial. You and distribute this negative. It's really a -1 times everything. Combine the y squared, combine the y, combine the constant. Use this backwards power rule integral to get the actual integral itself for each term and pull out the constants, and then you plug in -2 for y and then -3 for y and find that difference. Again, we will work that out, but that is the setup for the area. Okay, so that's great. Now we have y equals x squared over 2 minus 3x minus 1/2, and y equals 3. So we have this horizontal line and we also have this parabola. Now this is very interesting because we're not given any boundaries. So with this picture, I can see that we have our whole area being within this part and this part. Okay? But within that area, we have y equals 3, which is this horizontal line, and then this parabola, which is always below it, right? So in this case, actually, f of x is going to be y equals 3. So this is going to be this. And then g of x is going to be the parabola. So that means that within this interval, we have a clear top and bottom, but we don't know what that exact value is. So the integral is going to be my top, which is 3, minus my bottom function, with respect to x. But how do I know what a and b are? Well, according to the picture, I can see that it's -1 and 7, because it's nice and clear. But we don't want to just guess that. We want to actually be able to solve this. So what we would do is just find where these two are equal. So we just go ahead and do that algebraically. So we set them equal to each other, and you can solve this however you want. Perhaps just multiply by 2 over everything. So x squared minus 6x minus 1 equals 6. Then go ahead and move the 6 over. For our algebra friends here, I can really see that math does build on itself. So here you can backwards FOIL it. And we get either this equals 0 or this equals 0, so x equals 7 or x equals -1. I'm not walking through every single step, but that's to give you an idea. That's how we could get -1 to 7 if you're not given an exact, graph and where things are very clear. You don't want to necessarily guess, but in a pinch you can use your picture. It's labeled for a reason. But that's how we get our a to b values. And then we just have our top, which is 3, minus the bottom, which is this parabola function. And again, distribute the negative, and then go ahead and combine the constant terms and actually work out that integral. Plug in your 7, plug in your -1, find the difference, and you're good to go. Okay, so this is our little hard bit, and so the tricky part about this question is the figuring out what the bounds actually are. So sometimes you have to do the algebra there. Okay, and now let's work out this very last one. This is going to be a little tricky to color code here, but it's okay because all we need to do is rely on our picture here and our understanding of the fact that we are looking for an upper function and a lower one over an entire interval. So you can see we have 2 slivers here for our area. So we're going to have to look a little closer. We have y equals -x cubed over 2 plus 2x squared. So that's a cubic function. So that's this thing, like this. There's a negative coefficient, so it's this way, but normally they would look like this. And then we have a parabola again, but if we look closely over this particular interval from 0 to 2, we have the parabola being above the cubic. So for part of this is going to be f of x. For part of it, so from 0 to 2, f of x is going to be negative x squared plus 4x, and g of x is going to be the one below that. The cubic is below it, so that means that g of x is going to be the negative x cubed over 2 plus 2x squared. But then they flip, so from 2 to 4, they flip. The cubic is the other way around. Other way. So f of x is going to be negative x cubed over 2 plus 2x squared. And g of x is going to be my parabola. You can just see this from the picture here. So that means that our entire interval, or an integral, is going to be broken up into two parts, from 0 to 2 and then plus from 2 to 4. So what you don't want to do is write out from 0 to 4, because over that entire interval there is no clear top or bottom, right? Part of it is the parabola, part of it is the cubic function on top, and so you don't want to write 0 to 4, because then you won't know, and you especially don't want to just take this one to be f and this one to be g, okay? You have to actually break down the region. That means that this is going to be quite large to write out, but again, since they are nice and pretty polynomials, it's going to still be straightforward to calculate. So from 0 to 2, just follow your f of x minus g of x, and so we'd have negative x squared plus 4x minus parentheses negative x cubed over 2 plus 2x squared, and then plus 2 to 4, and I'll add the dx's here in a second, but negative x cubed over 2 plus 2x squared minus negative x squared plus 4x dx. So we actually have two integrals to work out here, but that's okay. That's okay with us. As long as we keep our bounds in the right order, we should be okay. So like I said, we'll use these setups to practice solving actual integrals with polynomials in another video. But I hope that this helps for actually setting things up. Sometimes, based on your question, you might even have a situation where your function ends up having a top and a bottom piece, and you'd have to break that up into like maybe a piecewise situation, or break it up in a way so that you do have a top and a bottom, and it might not be two separate functions. So other than that, that's all the different situations that I think might come up. But let me know as you work on stuff. I hope that this was a nice little review for you, or a little interesting study session, and if nothing else, I hope that you feel extra relaxed, and thank you for spending time with me. Of course, if you are asleep right now, I'm wishing you sweet mathy dreams. Here's a little Easter egg to my friends here on the channel who say that they never make it to the end of my videos. Love you. I'll see you very very soon for more math, okay?